Hi, in this video we're going to be talking about the quantization of charge and what that really means. For us to understand this, we're going to somehow dive, or if you may say, take a trip into the mind of the physicist Robert Milikan, who actually won a Nobel Prize for discovering the quantization of charge. He was also the one who made the experiment that we're going to be explaining, the Milikan Oil droplet experiment. Professor Roberts set up a really sophisticated apparatus, which you can clearly see here, and as you can see, it's really sophisticated. I've sketched quickly a simpler version of this so that we can explain things on. First of all, Professor Roberts set the two positive metal plates to be parallel to each other as shown here. So these two metal green plates, they were set up, he set them to be exactly parallel to each other. He would then introduce a bubble of oil, shown as the yellow dot here, between the plates. So this yellow dot right here was the oil droplet that he introduced into the setup. The professor would then turn on an X-ray tube that is shown in the grey in the drawing to ionize the oil droplet, and by ionization I mean to give it a charge instead of having a neutral droplet, and in this case the charge acquired by the droplet is negative. He would then turn on the variable voltage power supply, which is shown in blue, and he would start adjusting the voltage readings supplied to the plates to make the oil droplet suspend in the air. Since it's negative, it's obviously going to go towards the positive plate, and there's already weight acting on it downwards, so he would keep changing the voltage supplied by the power source until the object is in equilibrium. Now, since the two plates are parallel, they create a really uniform electric field, and by that we mean that the force acting on the oil droplet at any place is really constant. Now, if we look at the force acting on the oil, we find that there are only two forces acting. One is the weight of the object, which is acting downwards, and one is the electric field or electric force that is acting towards the positive plate, because we already said that the oil droplet was ionized to be a negative charge, and we know that negative and positive attract, so obviously the oil droplet would want to act towards the positive plate upwards and against the weight. Now, the value of the weight force is already known. We know that for any object the weight on it is mg, m times g, which is its mass times the gravitational field strength. Here the mass would be the mass of the oil droplet, and g would just be 9.81 because we are on Earth. The second force acting on the oil droplet is the electric field, acting opposite to the weight, meaning upwards towards the positive plate. Because remember, like we said already, that it was already ionized to be a negative charge, so it would obviously be attracted upwards. The value of this force, of this electric force, has a really interesting equation, and it is VQ over D. So if we have a look here, it's QV or VQ over D. The Q here is the charge of the oil droplet that we're looking to calculate, that we want to calculate. The V is the voltage difference between these two plates. So if I get a voltmeter and I connect it here, so I get a voltmeter here and connect it between these two terminals. I'm sorry, it looks weird a little bit. If you connect it between the positive plate and the neutral plate, the reading on this would be your V. so that's easy. The d is the distance between the two parallel plates. So I've shown here in red that this is the d, the distance between the positive plate and the neutral plate. Now for m, since the oil droplet is suspended in the air, we know that the force acting on it upwards is exactly equal to the force acting on it downwards. The reason behind this is because since the object is equilibrium, we know that the net force on it is obviously zero. So that means that the upward force equals to the downward force. So we can equate these two, QV over D equals mg, and with some manipulation we can get that Q equals to mgd over V. Now G, we know it, is 9.81. D, we can easily measure it using a meter rule. V, we can connect the voltmeter and it would tell us how much V is. But the tricky part is, how do we know the mass of that tiny little droplet? Well, its mass can be determined using the density times volume. If we look under a microscope at that oil droplet, we can calculate its radius and then calculate its volume using 4/3 pi r cubed, since the oil droplet is almost identical to a sphere. So we get the mass by multiplying the rho, or the density of the object, by its volume. The rho, or the density of the oil, is known, and V we can, like I said, calculate it using 4/3 pi r cubed. So we have our M, we have our G, we have our D, and we have our V. So Professor Milikan started calculating lots of values of Q. So he would try it with different oil droplets, with different intensities for the ionizing rays. He would change the V's here. He would alter so many different variables, and he would write the values of Q that he got. And he scribbled it on a paper and eventually got something similar to this. He got sort of numbers that are very similar to these. Now, can you spot any pattern that is occurring here? Like, can you see anything that relates all these numbers to each other? I'll let you pause the video for a minute. I'll let you think about it, and after a minute, why don't you return and we will talk about it. Okay, welcome back if you tried. As you may have predicted, indeed they're all multiples of 1.6 times 10 to the power of negative 19. So here 4.8 is 1.6 times 3, 3.2 is 1.6 times 2, etc. So Professor Robert kept asking himself, why can't I get any intermediate values, such as 0.8 or 5 or 19? Why can't I get except these discrete number of charges? Why, and more of that is, why are they all multiples of 1.6 times 10 to the power of negative 19? And from here he concluded that charge cannot exist in a continuous spectrum, which means it exists only in discrete numbers. And what that means is that you could only have multiples of this number for any object. The number 1.6 times 10 to the power of negative 19 is the smallest number of charge you could possibly have, and we call it the elementary charge, E. This is the smallest number that we could get for a charge, and we cannot break it into more parts. We can't also get 1.5 of that number. We have to get discrete numbers, so 3 times that number, 19 times that number. We can't get 1.5. And that is the theory of the quantization of charge. It says that it has to be, that the charge of an object has to be a multiple of of the elementary charge, which is 1.6 times 10 to the power of negative 19. And this is it, really. Thank you for watching. Please leave any questions if you have any in the comments section, and I'll try to answer them all. Cheers.